Hi, I'm Whitney Espick, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Thank you very much. For those who can see it, this is a brass rat from 1965. It's a real pleasure to be with so many alumni of MIT back in Kresge Auditorium. I want to give you, before I launch into the details of this presentation, a quick summary of what I'm going to say. The first thing I'm going to say is that the impacts of climate change, impacts on life, health, property, economies, and ecosystems are growing much faster even than was projected a decade ago. The second point I'm going to make is that this requires much more rapid action toward deep reductions in emissions and major investments in adaptation, preparedness, and resilience than was thought only a decade ago. That's the bad news. The good news is that the cost and efficacy of the remedies is falling rapidly. And the combination of increasing incentives to act and declining costs of acting is going to lead, in my judgment, to a political tipping point in which the political will that a number of speakers have mentioned will in fact materialize not only in this country but around the world. So let's look at a few details. I start with current science understandings supported by recent observations. So this is one of the most dramatic graphics for the purpose of convincing people that it is, in fact, human activities that have been changing the climate. This is 12,000 years of global average surface temperature based prior to the era of thermometer measurements on paleoclimatological studies looking at ice cores and the bubbles of gas trapped in ice cores over hundreds of thousands of years, looking at fossil corals, looking at sediments, looking at tree rings. And what we find is that for almost 7,000 years prior to the present, the climate of the Earth was gradually cooling. We were actually heading toward the next ice age. Starting around the time of the Industrial Revolution, usually taken to mean about 1750, that decline leveled off and then was sharply reversed. And you see on the right-hand side of this spike in temperatures, a rate of temperature increase quite unfamiliar over the geologic timescales of millennia. There's no question that it was human amplification of the natural greenhouse effect that created this reversal. The good news is we avoided another ice age, which might have happened 10,000 years down the road. The bad news is we overcompensated. Today, the dominance of human influence is very clear in the period of actual thermometer measurements, the period in which measurements by thermometers were pervasive enough to meaningfully define a global average surface air temperature. This is the period then from 1880 up until the present. One sees, as most of you probably already know, that the 5 hottest years in the period of thermometer records going back to 1880 were the last 5 years. The current temperature is about 1.2 degrees Celsius above the 1880 to 1890 average. And one sees as well, if you look at that longer history, that from 1750, the start of the Industrial Revolution, to 1900, natural cooling and human-caused warming were in rough balance. And the temperature didn't change very much over that period as a result. But the 20th century saw global warming become the dominant influence. Human-caused global warming became the dominant influence on the average temperature of the Earth. And a really key point, which still has not been fully appreciated by many people and certainly not by many of our political leaders, is that modest increases in average temperature lead to very large changes in heat extremes. This is just a fundamental characteristic of the normal distribution. You slide it a little bit to the right, in temperature, and what happens out at 2 sigma and 3 sigma, the events that were highly improbable under an unperturbed climate, become much more frequent. And that disproportionate impact at the extremes basically applies to any normally distributed climate-related variable. So it's not just temperature we're talking about, but many other aspects of climate. But let's look just for a moment, sticking with temperature, at the all-time high temperature records that were reached just in 2017 and the first half of 2018. These are the highest temperatures ever recorded in the specified places. In fact, in the last 2 years, worldwide, the number of extreme high temperature records set amounts to about 240 in different places around the world. And it is already the case today that working outdoors in the hottest months of the year risks heat stroke in many regions. And that is a problem that is going to become worse and worse. But warming also increases extreme downpours. This is one of the simplest in terms of the physics explanation of the impacts of a warming world. A warmer atmosphere can hold more water, and as a result, more can and does come down at one time. In addition, storm systems are moving more slowly in our warming world, and that's bringing more rain where these climate systems stall. And that, of course, leads to flooding. 100-year floods, so-called floods that used to have a frequency of once in 100 years, or 1% per year, are now occurring once a decade or more in many places. There were 3 500-year floods in Houston over the space of 3 years. These pictures happen to be from East Baton Rouge, Louisiana, where they got in August of 2016 up to 20 inches of rain in 3 days. In Houston, as you know, they got 50 inches of rain in 5 days. And of course, most recently, we've seen flooding in the Midwest. First of all, in March of 2019, setting new records for the region, and it is continuing as we speak today. Climate change is also worsening wildfires. A lot of things contributing there: heat, drought, more dead trees killed by pests that have been advantaged by climate change, and interestingly enough, more lightning in a warming world. And lightning is the biggest cause of wildfires. These are figures for annual area burned in the United States. You see there's a lot of year-to-year variability, but the trend is unmistakable. The average area burned has increased more than 4-fold since 1985. The U.S. fire season is now 3 months or more longer than it was 40 years ago. The average fire is much bigger and hotter than before, thus spreading faster, doing more damage to structure, posing more risks to firefighters. 9 of the 10 biggest U.S. wildfires in history took place since 2004, the other one in 1997. In Alaska, even the tundra is burning. Tundra used to be too moist to burn, but it's burning now. There's a picture of a tundra fire in Alaska in June of 2015. And smoke from today's big fires is harming health over enormous areas. This is a picture of the particulate air pollution from fires in the northwestern United States, extending in 2017 all the way across the country, producing severe air pollution even in New England. Thermal expansion and melting land ice, the ice from the Great Greenland Ice Sheet, from the Antarctic ice sheet, from land glaciers, and the thermal expansion of seawater has been accelerating the pace of sea level, not just increasing sea level, but increasing it faster, as you see here. In the middle to the last part of the 20th century, the rate of sea level increase was twice what it was in the first third of the century. From 1993 to 2017, it more than doubled again. And if you draw a separate line through the years since 2010, it's actually nearly doubled yet again to about 5.5 millimeters per year. Rising sea level is causing more coastal inundation. This is really quite astonishing, this graph. These figures are, with the exception of the lower long blue line, they're 20-year averages, 50 to 69, 70 to 89, 1990 to 2009, and then 2010 to 2015. The average number of flood events per year, flooding at high tide, in these locations on the east coast of the United States. You look at that rate of increase, it is astonishing. Warming also increases the power of cyclones. It does so for many reasons. I won't go through this whole slide, but the basic story is tropical cyclones get their energy from the warm surface layer of the ocean. That layer is getting both warmer and deeper under climate change. That means not only that more energy is available for evaporating water from the ocean surface, driving cyclones, but the fact that the warm layer is deeper restricts the self-limiting effect of cyclones of stirring up through their wave action cold water from the deep. The wave action is no longer reaching the cold water, and that's one of the reasons that typhoons and hurricanes are getting stronger. Of course, a lot of different factors affect the formation and the tracks of these storms, but the fact is that all else equal, a given storm is going to be more powerful in the presence of a warmer ocean with a deeper warm layer than it would be otherwise. And of course, higher sea level, on top of which the storm surges build, is further aggravating the damages from any given tropical storm. If you look at the observed strengthening of tropical storms, this is now observation, not theory. The largest, strongest tropical storms in history in virtually every ocean basin that experiences tropical storms have occurred since 2012. Stunning, really. This did not happen by accident. So what the science indicates is coming. I just flew back from Beijing yesterday. A week of conversations with Chinese colleagues about climate science and policy. This is a good quote from Lao Tzu. Temperatures are going to continue to rise. There's no question about that. Nothing we can do can stop the rise of temperature in its tracks. But how much they rise depends strongly on the future of emissions. On the left, you see projected annual global carbon emissions in a wide range of scenarios. The black line to the left is what has been observed up until now. The scenarios, basically the top red one is business as usual, not meaning that nothing changes, but the pace of change is about what it has recently been. And on the opposite end, the lowest of the scenarios examined in the last round of the Intergovernmental Panel on Climate Change Studies, green, rapidly declining emissions. And you see on the right the projected global temperatures that even under the very low emission scenario, rapidly declining emissions, the temperature still increases above what it is today. That's a result of the momentum in the climate system. It takes the ocean a long time to catch up with changes in the energy balance that we've imposed on the atmosphere. And then it takes, by the way, the ice a long time to catch up with the temperature changes imposed on the ocean. Sea level, as a result, continues to go up even after the temperature stabilizes. Absent big, fast emission cuts, we can expect record heat waves as the new normal. We can expect far more torrential downpours and flooding. Large expansions, further expansion in the area burned by wildfires, destruction of most of the world's coral reefs, wider disruption of marine food webs and fisheries, big increases in the frequency and intensity of droughts, more Category 3 to 5 hurricanes and typhoons making landfall, more sickness and death from heat stress and tropical diseases, falling agricultural yields, even accounting for continued technological progress. It will, under business as usual, be more than offset. The technological progress will be more than offset by the damages to agricultural productivity from climate change. And sea level rise that could reach 0.5 meter by 2050 and 1 meter or more by 2100 and 6 to 10 meters eventually. As a result of all of this, we will see much bigger flows of environmental refugees and the associated political and social tensions. So the implications for policy, what does all this mean for what we need to do? And I like this quote from my former colleague in the Obama administration, Jake Sullivan: "Between fatalism and complacency lies urgency." We have to avoid fatalism. We have to avoid complacency. We need a sense of urgency. And this is a complicated graphic, but it repays study. It shows just how deep the emission cuts need to be to avoid climate catastrophe. Emissions pathways on the left, characterized by reference no policy, reference low policy, Paris continued ambition in the middle, lower dark blue curve, Paris increased ambition, and below that, illustrative 50% cut, 50% chance of staying below 2 degrees C. 50% chance of staying below the target that was embraced by most of the world in 2009 and embraced by everybody in the Paris Climate Agreement in December 2015. The low policy case gives you just a 35% chance, well, I shouldn't say just, it gives you a 35% chance that the temperature increase would be more than 4 degrees Celsius by 2100. The Paris increased ambition case gives only about a 30% chance of keeping the temperature increase below 2 degrees Celsius, that internationally agreed target, by 2100. And you look in more detail, you see the probability of staying below 1.5 degrees, which was the aspirational goal embraced in Paris, because the countries most impacted argued in Paris that 2 is already a disaster for us. At 2 degrees, many of the low-lying island states will go underwater. For them, adaptation means evacuation. That's not very satisfying. I believe that having any chance of holding the temperature increase below 2 degrees Celsius will require, first of all, a price on carbon, a global carbon tax, starting soon, and escalating from around $30 a ton of carbon dioxide equivalent initially to at least $100 a ton of carbon dioxide equivalent by 2030. Ideally, it would be collected by national governments and rebated on a per capita basis, which would avoid the otherwise regressive effect of such a tax. And I will note, if you think $100 a ton by 2030 is extreme, that the recent Nobel laureate in economics, Bill Nordhaus, who received the Nobel Prize this past year for his work on the economics of climate change, thinks this has to be $200 a ton by 2030. I have more faith in technological innovation than Professor Nordhaus does, and that's why I think 100 will be enough. It would incentivize using the best available low and no emission technologies now, and it would incentivize investing in research, development, and demonstration to get the better technologies that we will need for the latter part of those deep emissions cuts through the latter part of this century. In addition, in order to be sure we get the technological innovation, we really need a massive program of innovation on clean energy and energy efficiency, advanced through partnerships among government, industry, and universities, and including all the things listed here, and they've all been mentioned almost without exception by previous speakers: cheaper wind and solar power, better electricity storage, carbon capture and sequestration for fossil and biomass power plants, sustainable biomass production for power plants and aviation fuel. It's going to be hard to run aircraft on batteries. Innovation to make nuclear energy expansion safe and affordable, that is nuclear fission energy, and the continued pursuit of practical fusion power. All these things should be done, and they should be done in partnerships. And those partnerships, by the way, should not be across sectors alone, they should be across nations. We should continue to partner with Russia, with China, with Europe, Japan, with South Korea, in all of these domains, because it is in the global interest to speed up innovation in these respects. We also need a similarly massive set of public-private university partnerships focused on developing and implementing adaptation measures to limit the harm from the changes in climate that can no longer be prevented. For years, some people have resisted talking about adaptation, fearing the discussion of adaptation would lead to diminished interest in mitigation, in emissions reductions. I think that is a misguided fear. I often say, in the face of the climate change challenge, we have 3 choices: mitigation, adaptation, and suffering. And if we want to minimize suffering, as should be society's goal, we are going to need to maximize both mitigation and adaptation. Mitigation alone won't work because the climate change is already occurring, it's already doing damage, it will do more before we can bring it to a halt. Adaptation alone won't work because adaptation gets more difficult, more expensive, and less effective the larger are the changes in climate to which you're trying to adapt. We need enough mitigation to avoid unmanageable climate change and enough adaptation to manage unavoidable climate change. I think that the political will that we need to get all this done could materialize faster than many think as a result of the combination of rapidly increasing damages and declining costs of remedial action as a result of innovation. That combination is going to make ever clearer that action is much cheaper than inaction. Thank you very much.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.